Valence bond theory. Valence bond theory is a model of bonding used to explain the three-dimensional shape of atoms in a molecule. We've talked about a Lewis structure, for example, CH4 would be C with 4 hydrogens around. We've talked about how that shows how the atoms are bonded around the central. Then we talked about Vesper Theory, which says that since bonds have electrons, there's repulsion going on, and the bonds actually bend in different directions to give a different shape. Now this, because this has 4 electron groups, has a tetrahedral shape. Now, these are both a little vague because if you actually think of the electrons in the outermost shell of carbon, we have a 2s, which has a filled orbital, and 2 p's, which have 2 electrons in it. So technically, there's only these 2 electrons that can bond with a hydrogen. So where does a tetrahedral shape come from? This brings us out to valence bond theory. Valence bond theory was designed to actually explain the three-dimensional shape of the different atoms and molecules to help explain their properties. It's most common in carbon, nitrogen, and oxygen because mainly most compounds out there are made of different carbon, nitrogen, and oxygens. Valence bond theory works through something called hybrid orbitals, or hybridization. Hybridization is the bending of 2 different varieties, essentially. So you could think of a horse and a donkey coming together to make a mule. That's hybrid. So here we're going to make hybrid orbitals to explain the three-dimensional shape of different atoms. So if we look at the actual energy distribution of carbon, we have, looking at just the valence shell electrons, 2s and 2p. Now again, this doesn't make sense because we only have 2 unpaired electrons in the valence shell, so you would think that only CH2 exists, for example. However, experiments have been done to show carbon always wants to have 4 bonds. That is the most stable form of carbon, when it has 4 bonds connected to it, an 8-electron valence shell. Well, the way to do that is to hybrid these 2 valence shell orbitals together. This would create 4 2sp3 orbitals going in 4 different directions for the tetrahedral shape. We have 1, 2, 3, 4. Note that the energy of the hybrid orbitals is in the middle of the 2 orbitals that were put together, essentially. So this helps explain the three-dimensional shape of the Vesper theory. Remember that a 1s orbital, let's do it in a different color, is a sphere. And then the 2s orbital is also a sphere, but it's larger. And then you have your p orbitals. You have your py, your px, your pz. So the overlap allows the electron to pair 4 hydrogens with the carbon. And experiments have been shown when carbon is bonded to 4 different atoms, it lowers in potential energy. This brings us back to Coulomb's law, knowing that things want to be paired because they lower in energy, they actually become more stable paired together than when they're separate. So having these hybridized orbitals makes carbon more stable than when it's not hybridized. How would that actually look? So if we showed you the bonding of the carbon, you would have your carbon, and now your tetrahedral shape, your 4 orbitals. And then you would have the s orbital of each hydrogen that would overlap to make the bond with the sp3 orbitals of the carbon. Now here's a better picture of that. Right here you can see the carbon in the middle and these three sp3 orbitals. They are bonding with the s orbitals of hydrogen, giving you a pair of electrons. Sometimes the spin of the electrons is confusing to students, but electrons will shift in the way to pair when the orbitals overlap to form a bond. Now, what about when you have a lone pair? So carbon, simple enough. What about NH3, ammonia? We know that ammonia, nitrogen, wants to have 3 bonds with a lone pair on top of the nitrogen. This is a trigonal pyramidal shape molecularly. However, it also has, and still is, tetrahedral for the electronic geometry. So 4 things around that are electrons. Where exactly does that apply here? So if we look at nitrogen, we have our 2s, which is filled. And then opposite spin. And then we have our 2p, which is, we have how many electrons? 5. So we have 3 unpaired electrons in the 2p. So here, it would make sense, all right, well, I have my 3 unpaired electrons in 2p. I have my 3 bonds, so why do I need to hybridize? Well, there has to be room for the lone pairs also in the outermost shell. So these also hybridize to form 2sp3 for all of them. I'm just going to write it once. Where if you fill your electrons one at a time with your 1 pair to give you 5, the pair represents the lone pair of electrons in that sp3 orbital. And the other unpaired electrons, half-filled shells, represent the bonds. Now, to make the tetrahedral shape, the hybridization had to occur so that there can actually be 4 things around the nitrogen. And that would look similar to the carbon, except one of those bonds would then be a lone pair in the orbital. Now, that overlap here is called a sigma bond. When you have a direct overlap of bonds, you form a sigma bond. That's always in single bonds, and there's a diagram of that here. So when you have, these are the p orbitals, excuse me. When you have an s orbital, for example, and another s orbital, the direct overlap is a sigma bond. Always in single bonds. So here, in ammonia and carbon tetrahydride, CH4 methane, you always have sigma bonds. Now, what if you have pi bonds in there as well? So now back to my diagram over here, you can have different types. We know that we have px, py, and pz. Note that different areas can name what the px, py, and pz is. The purposes of our book, we say that px is along the axis, and they overlap only once. And that one overlap, that head-on overlap right here, is a sigma bond. Now, for the py and the pz, because they're inner and out of the plane, they will kind of combine and overlap here together to form a pi bond. Now, this will occur when you have double or triple bonds. Now, let's see when that would come into play. So, for example, let's look at C2H4, adding some carbons and some hydrogens. Now, again, carbon is a central atom. We have 2 carbons here. And if we look at the Lewis structure, you have carbon and carbon with 4 hydrogens around. hydrogen, because it only has the one electron, can only bond once, and you give the double bond to carbon. So this is completely symmetrical, and both carbons will have the same hybridization. So you can just figure it out for one of them. So you have the energy, and you have for carbon. We have our 2s filled shell and our 2p2. Now, how would this be hybridized? Because technically, you have 3 electron groups. So this is a trigonal planar shape. Even though there's a double bond, the space with electrons around these atoms is 1, 2, 3. So 3 groups, so trigonal planar. So we wouldn't have sp3 hybridization. How does that work, especially when you have a double bond? So, following all the rules that we have discussed in previous chapters about filling in the electrons, one at a time. So you take your 1 from the 2s, and another one from the p and the p. So you have your 3. This will be sp2 for each of these. You can write the 2 in front. You'll see that sometimes just to indicate which energy level it is, because we have 3, 4, etc. Now this explains the bonding of the sigma bonds, but there's still that 1 electron we haven't used yet, and then that will be your unhybridized p orbital. And that p orbital then actually forms with the orbital of the other carbon to then give it a pi bond. So let's look at that. So it's going to be kind of messy, but if we have carbon and carbon, and then we have the hydrogens around, it's very unsymmetrical. Let me fix that. Okay. So sp2, trigonal planar shape. So we will have the 1 sp2 or orbital here. One here, one here. And then same with this carbon. These are sp2s. I'm going to change my color for the p. Now, I have my sp2 orbitals, and then I still have my p orbitals. And then I have the s orbitals of hydrogen that will overlap. Now the s orbitals, the p orbitals, they will overlap here to form a pi bond. So you have your sigma bonds, and you have the pi bond, which then gives you that double bond and the sp2 arrangement of the electrons. Now another example of this could be CH2O. We know carbon, hydrogen, and oxygen. That will double bond. So this, again, if you look at the carbon, has a trigonal planar shape. The double bond will also have a sigma and a pi bond, and will have sp2 hybridization. So it should have a very similar picture to the one drawn, except for you only have one central atom. So let's look at the picture. Picture's over here. And let's see if I can make this a little bigger. And you can see that you have the purple, which are the sp2 orbitals. You have the p orbital of the oxygen that overlaps with the carbon here. And then you have another p orbital that overlaps with the carbon p orbital that was unhybridized. And then you have the hybridization orbitals with the hydrogen as well. And this is just a good representation of where that three-dimensional shape actually is coming from and indicating all of the bonds, not just single bond arrangement. Now let's look at one more common one, which is sp. Now, what if we have C2 two H2. So I have carbon and carbon and a hydrogen and a hydrogen. This will give me a triple bond in the middle. Now again, this is completely symmetrical, so you could look at one carbon at a time. So if I look at a carbon, again, 2s, 2p. Now here I have two electron groups. I have a linear shape. Well, I mean, I have the two electrons that are unhybridized. So does that make sense? Does that give me my linear shape? Well, not really, because those are in the p orbitals. They have to be just completely around the central atom. So what happens here is the hybridization will be 2sp for all of them, with two unhybridized p orbitals. And those unhybridized p orbitals will form the triple bond. So you will have the carbon, carbon, hydrogen, and hydrogen. We know hydrogen will have the S, and carbon will have its sp, and then, to be consistent with the picture, we have a pi bond that forms because of the p orbitals, and you have another pi bond that will form because of the other p orbital that was unhybridized, which will then give you your two pi bonds and all the sigma bonds. Let's see if there's a better picture. Right over here, you can see that you have your hybridization orbitals right here. You have one of the pi's, then you have the other, and you have your sigma bonds. So this is the whole point of hybridization. It's to understand, okay, how many electrons do I have to have available in the hybridized orbital? So if I'm linear, I have to have two unfilled shells. So it's sp. And then, because of that triple bond, there's unhybridized orbitals. But without even realizing that's the triple bond, we have 4 electrons here. 4 things of orbitals, the 3 from the p's and 1 from the s. So if you're hybridizing 2 of them, you will have unhybridized. Now there's a few others that then explain the other shapes that we've seen. So if we look here, down here, this just further explains the different shapes of the molecules that you can see. So we've talked all the way up to 4. If you then have 5 electron groups or 6, you will also then have the d orbitals in there to make more space for the bonds and the electrons, whether it's lone pairs or not. So it's really important to determine what shape you have, and then basically piecing the orbitals together. So if you had S, P, and D, you would have your, starting at 3, your 3s, your 3p, and then 1, 2, 3, 4, 5, your 3d. And then that would hybridize to your sp3d or sp3d2. This would give you the 5 electron groups. This would give you your 6, where you would still have unhybridized to make room for the lone pairs that you have around the central atom. Valence bond theory, the purpose is to help explain actually what's happening, because it's not just 2 dots in a bond. There's actually these electrons are in regions of space, and how these regions of spaces are actually orbiting around the atom and how the electrons are actually bonding together is what valence bond theory helps explain, where the shape is coming from through the overlap of the different orbitals when atoms come together in molecules.